Okay, great. Thank you. You hear me okay? Oh, okay, great. That's really loud. Okay, well, thanks for attending, everybody. My name is Kevin Keryk. I'm with Avnet. We're a partner with Xilinx on the Ultra 96 board that you see here. This is my first time presenting at Lenaro Connect, so thank you for inviting me. And I had lots of interesting discussions so far about the things that we do in conjunction with Xilinx. We're the global exclusive distributor with Xilinx, so that's how we got partnered in with the Ultra 96 board. We put together a lot of the reference designs that you see up on our Element 14 website and our ultra96.org website. I'm here to talk to you a little bit about security and some of the special security features that you'll find inside of Zink Ultrascale Plus, and hopefully, start a discussion with some folks around how we can improve our engagement with the open source community. So I'm sure all of you have heard the story about security. Security is important for everybody, and I'd like to help understand how we can participate better in what is going on inside of the Lenaro community so that we can get better security on Ultra 96 designs. So I want to start out by just talking a little bit about the history of Avnet's engagement with Xilinx around our design. So back in 2011, Xilinx introduced Zynq 7000. We were partnered with Xilinx on creating the Z board design. They came out with a reference design that showed how to do secure boot, and they showed that off at the Xilinx Security Working Group in the fall of 2012. There was an app note that was released called XApp 1175, and that showed how to do secure boot on Zynq 7000. And based upon the feedback that Xilinx got for the security on Zynq 7000 family, they've made some significant improvements to Zink Ultrascale MPSoC family. So that was released in 2015, and shortly after that release, Xilinx engaged with Avnet and Infineon as a partner, and we worked together on creating a new measured boot app note that took it a little bit further than what the old app note did for Zynq 7000. And since then, they've released yet another app note called XApp 1323 that shows how to the steps that you need to take in order to create tamper-resistant designs. And this all steps towards this IEC 62443 compliance that everybody's looking for in the industry. So IEC 62443 is a standardization, so it involves several different layers. Mostly we're focused on the system level layers here at Avnet, since we fit more into like a value-added reseller step. Xilinx would fit more into the lower level layer with the component and making sure that they deliver features on their chip that would enable those types of requirements to fit the standard. So just kind of elaborate a little bit on the XApp that we've released. We did create a cybersecurity concept design in conjunction with Avnet, Avnet in conjunction with our suppliers Infineon and Xilinx, so they show up down here at the bottom. So Xilinx, they bring to the table the Zink Ultrascale MPSoC, the same chip that's found on Ultra 96. Infineon, they have an Optega TPM. I'll show a few of the different ways that you can get the Optega TPM on your 96 boards hardware. But Avnet, we're not just a distributor, we also helped bring a few of these different pieces together as part of a system solution. At the time we were working with a partner named Okana, that was one of Infineon's partners on doing the security, and we created an industrial grade IEC 62443 compliance concept design that shows how you can securely boot a system, you can provide measured boot on a system, and then we showed how to run Azure Cloud Services on top of that in containers. So in order to do this, we needed some hardware at the time. Traditionally, the module format that's worked really well with Xilinx development boards is a format called Pnut, and that's a format that was spearheaded by Digilent. And so here you see a Pnut that we worked with Infineon on creating. It has the SLB 9670 TPM 2.0 device on it. It's available today from the Avnet website. I have one here. I have one that's hooked up to my Ultra 96 board in my lab, so I didn't want to disturb that, but I have one of the early prototype versions that has the TPM 2.0 firmware loaded on it. But what I did is I was able to find these little headers that plug into the 96 board, low speed expansion port, and then I was just able to solder these wires onto it and get that up and running on my Ultra 96 board. But it's something that we have available at Avnet. I did a little bit of research. There was a presentation that was done by Joachim Beck at the SFO 17111 Secure 96 session, and I put the YouTube video up there if you want to take a look at his session. But we're not the only ones who are focused on security. There's been other people that are looking into this, specifically from a Lenaro perspective. This one has a few more features than just the SLB 9670. There was a few Atmel devices that were on there. Interestingly enough, I went to go purchase this board to bring one for show and tell at this conference, but I can't find them stocked anywhere. Amazon says that they're all out of stock, and you can get on a waiting list to get some more. And then I did a little bit more research, and I found this board from our competitors at Arrow. So they have this showing at the Arrow table. It has the same parts on it. It's called Tracor. It's a little bit more expensive than the other options that are out there, but it does have those security devices, so if you're interested in doing security stuff, you can find the hardware in a number of different formats. So today I'd like to shift gears a little bit and talk about how we can establish a hardware root of trust using Zink Ultrascale MPSoC features that they have inside of the processing system. One of the unique things that Zink Ultrascale brings to the table is it has this programmable logic piece, but since it's a processor first solution, you can't get the programmable logic up and running until you get the processors booted first. And so that's what I'd like to talk a little bit about today and focus on security measured boot. So here's the Zink Ultrascale MPSoC block diagram. It's got quad A53 processors. It's got dual Cortex R5 processors. But it has, in the middle here, these two special pieces. One's a platform management unit that can help you with system management and doing power management. And another one is a thing called the CSU, and that's the configuration and security unit. And it has the trust zone access inside of it. It has voltage and temperature monitoring, so you can do tamper monitoring on your device, and you can take countermeasures to basically disable your system so that nobody can get your secret keys out of it. But this CSU is an important part of getting the system up and running and booted securely. So before I move on here, make sure I got everything covered. So one of the few of the features inside of the CSU that are important, it has a RSA 4096 asymmetric algorithm built into it, and there's an API that allows you to access that from software that's running on the other processors. It has a hardware accelerated SHA-3 384 engine, and there's also you also have the ability to implement a SHA-2 256 software implementation on there to help provide security on your other piece of the system. And the confidentiality on the system is provided with a 256 AES GCM engine. So I'd like to take a little bit of time now to focus on this diagram. This is a diagram that you can actually find inside of the source document, user guide 1085 that Xilinx publishes. But it shows you a high-level overview of how you can boot a system securely and establish a hardware root of trust on your Zink Ultrascale system. So on this system, basically on the left side, we have these processing units over here. So we have a PMU, the CSU, the APU, the RPU, and the PL. The PMU, that's the power management unit. It's a triple redundant microblaze processor that's hardened inside of the die. CSU is the same thing, but it is booted from a metal ROM, so you can't change the firmware for the CSU. The APUs, those are the quad A53 processors. The RPUs, those are the Cortex R5 processors. And then there's programmable logic, which you don't find on some of the other ASSPs that are out there. And I have another course later today that's going to talk a little bit more about how you can create custom accelerators that go into the PL. But I want to highlight this piece here, right here, is that PL is where your IP is going to go. That's where your company's intellectual property is, and you don't want people going in and reverse engineering your product and understanding what it is that you could do, because then they can clone that and copy that onto other systems. So a key part of booting a secured system is being able to authenticate and decrypt the programmable logic bit stream that goes inside of the configuration RAM. So now I mentioned configuration RAM, let me cover what's on the left side of this diagram. So on the left side of this diagram, we have all the different memories that are available to the processing system. Starting at the top, we have a separate PMU RAM space. There's a configuration security unit RAM space, and there's OCM, which is on-chip memory. It's a piece of fast RAM. And then there's configuration RAM down here at the bottom. And these are all in gray because these are all mostly secure pieces of RAM because they're all on the same silicon as the processing unit. So in order to get access to them, basically have to strip the chip down and probe on the die in order to get access to that RAM. The DDR is off-chip, so that one's a little bit more unsecure because you can have easier access to probe that with a logic analyzer. You can kind of see what's going on DDR. So when you're booting your system, you want to keep in mind if there are some things that you don't want exposed to the outside world, make sure that you're loading it onto one of the on-chip pieces of memory rather than the external DDR. So if I start following this flow diagram, you basically, after power on reset, the processing up in the upper left-hand corner, the power management unit boots from its ROM. That's a bare metal ROM. And one of the first things it does is it releases the configuration security unit from reset. And that allows that CSU processor to begin executing from its hardened metal ROM. And its job is to first load the first stage bootloader, the FSBL. So the FSBL, that's a piece that has traditionally been a Xilinx provided proprietary piece of code. They've gotten a lot of feedback over the years from folks that won't touch anything that's not open source software. And so they have released a version of that first stage bootloader code that is, I believe it's under the GPL. And so first thing you want to do is you want to load the first stage bootloader. The first stage bootloader knows how to load the other pieces of memory, and it knows how to load them securely. So it can authenticate and decrypt some of the other pieces. So one of the things that it's going to do next, you have the option of loading PMU, the processing power management unit, with a piece of PMU firmware. So that's up at the top. And if you when that's loaded, it gives you access to some libraries that I'll talk about at the end. But basically, it gives you a ZIL FPGA library that allows you to configure securely the programmable logic bit stream. It gives you a ZIL Secure library that gives you access to the hardware accelerated crypto engines. And it also provides for doing power management framework, so you can power up and down different power domains for doing power savings. You can do warm resets and things like that. But all that firmware gets authenticated by the CSU. The other job of the first stage bootloader is to begin booting the rest of the system, including the application processor. So in order to do that, once that first stage bootloader gets loaded, it can load the ARM trusted firmware, it can load U-boot, and then it can also load the bit streams as well. And the first stage bootloader, it executes out of on-chip memory for security reasons because it's providing the authentication and decryption of those other pieces of code. So the ARM trusted firmware, that's also going to execute out of on-chip memory as well. So that's this ATF block right here. That one is responsible for setting up your trust zone and the other pieces of ARM IP that's on this chip. Once you get U-boot up and running, let me skip the U-boot portion, and because the bit stream usually gets loaded next. So the next step of the first stage bootloader is to load the bit stream, and you can do that by authenticating or decrypting that bit stream inside of external memory, or if you want to be really secure, you can load it out of OCM. It does take a little bit longer to do that if you have a large piece of programmable logic, because you have to decrypt it a block at a time, and instead of doing it all at once. Once you get the programmable logic bit stream up and running, then you can then load U-boot on the system, and then U-boot can continue booting up Linux like a normal embedded Linux system. It can also load RPU software inside of the real-time cores. So if you have like a real-time operating system or something that's part of your system, you can load that into the RPUs at that stage as well. So here's some more resources on this. These are the three key libraries that I had mentioned before. So there's library documentation. It's under this link right here, where you can go to find out more information. So the three ones that you want to keep in mind are ZIL FPGA. So that allows you to do the secure loading of the programmable logic bit streams. And so there's certain steps that you can take in order to perform that. ZIL Secure, that one provides for secure loading of software and crypto accelerators. And there's a whole entire reference on that. There's a ZIL S-Key library, and this allows you to, from the processing units, program the battery back RAM, so you can load your security keys inside of there, or you can also load your security keys inside of eFuses, and that provides an API interface for programming that from the application processors. Another place where you can find more information is the Zink Ultrascale MPSoC Technical Reference Manual, and that's User Guide 1085. That's where I was able to find the documentation for doing the secure boot. And then there's also a newer document. Oh, it's not a document, but it's a website that lists all the various documents that you might need to reference in order to securely boot your system, and that's this Design Security Hub, and that's available on the Xilinx website as well. So that brings me to the end of my presentation. So I just want to thank the following people for their wisdom and encouragement to put together this presentation. I get a lot of questions about doing security stuff, and there's not a whole lot of information out there, and I tried to condense this down into a quick reference for people to look at and evaluate how they can get the security that they need on their Ultra 96 board. So first of all, Fred Kellerman, he works in my group. He's given me a lot of inspiration to go ahead and put this course together. Jason Moore at Xilinx, he gave me a lot of information on where to go to find this information and distill it down into a single presentation. And Bruce Schneider, I've been reading his book for quite a while and try to understand all the different vocabulary that's used in the security world to try to decipher a lot of this stuff. So I want to thank everybody for attending my presentation. Looks like we ended a little bit early, so if you guys have any questions, I'd be happy to answer them. If not, we can go ahead and wrap it up. Yes, sir.
You mentioned several steps where you load the firmware, this first stage bootloader, and then the AP firmware, but you didn't mention where it's stored. And so, do you have any protection on each stage? Do you have different location for first stage bootloader and firmware, and for application core firmware? Or they stored together? And can you explain how this firmware is stored?
Yeah. So if I understand the question correctly, you're asking. I showed where they get loaded to. You're asking where do they get loaded from when the system's booting up?
Right. You explained how it loaded, but another security thing is where it's stored and how we protect the actual images and verify what those images are correct and can be executed on the system.
Yeah, no, that's a really good question. So for Zink Ultrascale, you have a number of different boot memory options for non-volatile memory. You can boot from QSPI memory, so external QSPI memory. You can boot from eMMC is another option. We have a lot of folks that are booting Ultra 96 from a SD card, which is not particularly secure because somebody can walk up and swap out the SD card with something that has something malicious loaded to it. So those images, I mean, there's very little that you can do to protect that information on those RAMs because anybody can walk up and just read the information off of the memory and see what's on the memory. So that's why it's important to encrypt those and sign those images before they get loaded onto those memories. So that way, if you're reading it off, you're reading off a bunch of information that doesn't really make any sense in terms of execution instructions until it gets decrypted into those memories.
So do you have any like a platform root of trust, like a hardware root of trust, like, I don't know, store the key somewhere?
Yeah, so the keys, if I back up here a little bit, the keys actually get stored inside of the Zink Ultrascale device itself. So they're stored inside a subsystem underneath that only the CSU has access to. And those those you can store them inside of two options on this device. You can store them either inside of an eFuse inside the device by blowing hardware fuses, and you can program your secure keys into there. There's also battery-backed RAM that you can store your keys into as well. And then you can also use, I mean, if you're really concerned about somebody trying to get your keys out by doing like differential power analysis or something like that, you can use the voltage and the temperature monitor on the device in order to monitor whether or not somebody's tampering with the device, and then go back and wipe out that memory. And then you're basically bricking your system, but then you protect your system from being compromised by somebody figuring out what the keys are.
Do you have a feeling for what the boot speed, is there any significant effect on adding the crypto?
It definitely does affect the boot speed. When I was doing some research, I had the same question myself. So that's why I put this thing up here. If you go onto the Design Security Hub, they have a whole entire document. It's basically like an Excel spreadsheet that says, like, if you have this option enabled and you're using this particular boot methodology, it will take you about this long. So it definitely takes longer. It's something that you can roughly calculate based upon the size of the image that you're decrypting. And they do have some documentation on that is significantly better than what they had for the Zynq 7000 family, but it's all up on their website. Okay, great. Any other questions? Yep.
So the real-time CPU is running on DRAM, right? So anything can be seen, right? I mean, it's external, so anyone can decipher whatever you're doing there. So only the PL is protected, the execution, the bit stream.
Yeah, so the question is for the RPUs, the real-time processing units.
I'm assuming that Linux code and whatever applications or drivers, it's not really secret, but usually you put more secret stuff or proprietaries on the real-time CPU, right?
Yeah.
So from this diagram, it doesn't look to be safe.
Yeah, so the question is that if your secret sauce is in the code that's running on the RPU for doing the real-time stuff, is there a way that you can protect that? So there are some things that you can take. You're kind of limited in what you can do. You can, if there is secure like execution code, I believe you can store that secure execution code inside the on-chip memory. There's not an unlimited amount of on-chip memory, so you kind of have to partition that and evaluate which code pieces you want to load into on-chip memory versus DDR. But I don't know of any way of encrypting what's inside of the DDR. I haven't seen anything like that inside of the architecture. So if that's something that is important to you, then I think the recommendation would be to execute it out of the on-chip memory, because then that makes it a little bit more harder to figure out what's going on in terms of execution code.
But then if someone manages to break into your DDR, I mean, the real-time CPU code, he can jump to a separate code that he put there, and it will be accessing the secure. So it's not really closed. I mean, you need to probably put all the real-time stuff in a not on DDR, on SRAM or something. So
Yeah.
In the silicon.
Yeah, so what you're saying is that if somebody were able to compromise one of the other application processors and run their own rogue code on that, then they could theoretically go and then copy your application code that's running on the RPU into DDR memory and then inspect what's going on inside the code that way. I think that is an attack vector. I think one of maybe the countermeasure that we have evaluated is to enforce that you're running measured boot code on the other application processors, so that way you're running your own software and not somebody else's malicious software on those. So I think that's one countermeasure that you can take against that. Okay, great. No, these are all really great questions to ask. Anybody else? Okay, great. All right, well, thank you very much for attending our session, and enjoy the rest of your time here at Linaro Connect.